Hello, today I'm going to be doing a primer on Fourier and wavelet transforms, which I've been alluding to, but I'll make them conceptually a little bit more clear. I'll also be talking a little bit about how they pertain to the graph signals that we're working on. In signal processing, it is very common to look at signals that vary in space, time, or other regular substrate. Here you basically have an ordered time index in this audio signal and the amplitude of the audio signal at each one of these time indices. This kind of a signal can be Fourier transformed as follows. You basically take the integral of this signal from negative infinity to infinity, and the signal is encoded as a function of time, f of x, and it is taking an expected value with this function right here, which based on Euler's formula is the cosine of 2 pi kx plus I times the sine of the same quantity. So it's decomposing it in terms of these kinds of oscillatory signals if you use different values of k right here, which pertain to different frequencies. The way that's used is to decompose the signal into different frequencies. And so here you see this two frequency signal being decomposed into the sum of a lower frequency signal and a higher frequency signal. Usually we actually don't have the functional form to compute this full integral. So what we actually compute is called the discrete Fourier transform, or DFT. The DFT just uses n samples of both the signal that you're looking to analyze and of these oscillatory waveforms that are cosine theta plus I sine theta at n different intervals. And you can still do it at a particular scale like this. And typically you have many scales that you look at this with in order to get a rich set of Fourier coefficients. The DFT amounts to actually a matrix multiplication. So you have the Fourier basis signals sampled at n different time indices, and you're taking the dot product of those with the signal that you've measured, and this will give you the Fourier transform of those signals. Fourier transforms have numerous uses. They can be used in power spectral analysis, which means looking to see where most of the energy of the signal is concentrated, which frequency is it at. Solutions to differential equations, to edit and process audio and images, also for artistic purposes, and so much more. And so it's really lucky that we now have an analog on signals that don't occur on such a regular substrate, like a graph. We've already talked about how almost any data can be modeled as if it lies on a graph. And so for these data types, we can use the analogous graph Fourier transform, which involves using the eigenvectors of the graph Laplacian as the signals that we're decomposing our signals into, or the bases. But there is one disadvantage to doing this, and that is that Fourier transforms capture global frequency information, basically frequencies that persist through the entire length of time. But what if you are trying to decompose or represent sets of signals that have very bursty behavior, or they have frequency domain changes along time? These might benefit from a more time-localized frequency domain analysis. This is where wavelets come in. Unlike a sine or cosine function, these don't oscillate forever. They are flat, and then there's sort of an oscillatory blip, and then they flatten out again. So that means they're localized somewhere in time. And so what you can do is you can create a whole dictionary of wavelets out of your mother wavelet, which was here, by scaling the wavelet. So you can scale it with some scaling factor that squishes or stretches it, or you can shift the wavelet over in time to have it localized somewhere else. And shifting and scaling are the basic operations that can be used to create a whole dictionary of wavelets, and a discrete wavelet transform will decompose your signal into that basis. So you see that each wavelet is being shifted all over in time. It's also being scaled or dilated, and you're trying to catch where your signal matches with a particular wavelet at a particular scale and a particular time localization. So the wavelet transform also has a continuous and a discrete version, and again, we usually use the discrete version. In the discrete version of the wavelet transform, we would use very specific scaling and shifting of the wavelet at particular intervals, and we get wavelet coefficients as a result as a new descriptor of the signal. And this can have applications to time localized phenomenon that you want to find in any kinds of signal you measure, and a typical example being EEG signals that people measure on patients. If you're having, for example, an epileptic seizure or something, it's definitely localized in time. You can use wavelet transform to try to localize it. But can we implement this concept of a more localized oscillation that we want to find in our graph signals? And the answer is yes, and more so that we can actually use the diffusion frameworks we've been talking about. Remember that diffusion kind of spreads a signal out the more steps you go. So what you can actually do is you can start with a very contracted signal, which is just one at one vertex of your graph and just zero everywhere else. And as you diffuse that signal, meaning as you apply the diffusion operator to that signal will spread out, sort of like wavelet dilation. So what you can do with this understanding is you can actually create oscillatory wavelet forms by taking the difference between two dyadic scales of diffusion of a signal. So what you have here is a lazy diffusion operator, because a lot of times when you get just graphs that exist as data, for example molecular graphs, they don't have self edges. So you add the self edges on there and you get what's called a lazy random walk. Take this lazy random walk operator, which is basically an average of an identity with your original Markov operator, and you raise it to dyadic powers, and you take their differences, and that gives you a whole dictionary of these wavelets, and you can localize them by multiplying signals that are Diracs at different vertices with them to get your whole dictionary of wavelets. And this was proposed in a paper by Professors Koifman and Maggioni about 10 years ago, but more recently these have become very useful. So just a couple of years ago, there was introduced something called a geometric scattering transform. This geometric scattering transform is sort of a multi-scale wavelet transform of several signals, several Dirac signals that you send around different vertices, and then you take different scaled wavelet transforms of those and you collect them using nonlinearities such as statistical moments or averages. Then what can you do? You can take these first level wavelet coefficients or scattering coefficients, and then you can perform a second level of wavelet transform on those wavelet coefficients as signals themselves. So it turns out that this gives very rich information about graphs, because you don't even have to have any features on graphs. You just put these Dirac signals on graphs and you look at how they diffuse at two different scales, take their difference, and that already gives you rich information. But now you're doing it at many scales and several levels. And so this is giving you a lot of very detailed information about graphs. And as a result, the graph scattering transform combined with a simple SVM classifier outperforms a lot of deep learning models in terms of graph classification. And not only graph classification, you can look at those coefficients and actually tell, for example, which graphs are more similar and more different to each other. This is an experiment that was performed on graphs pertaining to enzymes of 6 different classes. And actually, these 6 different classes of enzymes have evolutionary relationships with each other. They're just off by certain mutations. And those evolutionary relationships and similarities between enzymes were the best inferred by, again, the graph scattering transform. We've tried it in our lab to encode non-coding RNA and protein signals, and here's just a toy data set we tried. We started out with a single graph, and we just modified that graph one edge at a time randomly. So basically we have a whole trajectory of graphs, and the fact that this is a single trajectory of graphs is only picked up by an autoencoder embedding of graph scattering coefficients. Graph neural networks, graph VAEs give you very noisy signal of this sort, and other embeddings like just the WL kernel or graph edit distances or graph scattering coefficients with PCA are not giving you informative embeddings at all. So this says that the graph scattering coefficients, dimensionality reduced in intelligent ways, can give you a lot of rich information about the underlying graph. And so hopefully you're convinced now that graph wavelet transforms are important as well.